Good afternoon to you all. Today I will be talking on the sphere of materials around us. You will be surprised to see what is materials and what is a matter. So simple example is, since I wanted to introduce this because it is a seminar for students and teachers. So anything which has a mass and we can and it is tangible to us, we call it matter. But any matter that we intend to use, we call it materials. So whenever we say materials, that refers to those matter which has a specific purpose in our life. Okay. So if we see, we as people, we live in buildings, we use bridges, we use aeroplanes, rails, towers, all these products what we know in our life. They are the product of several years or decades, or you can say centuries of research work by our predecessors. And what I am going to do is I will be talking about some of the materials and processes which give products. For example, any material what we have that gives rise to products, and a product requires to have some properties, some shapes, and these properties and shapes are given to materials by using some processes. So in this talk, I'll be mainly talking about the materials and what are the processes. And basically, I will take up advanced processes which is used to give shape and the property to the materials which we use. But before going to that, since this topic, this seminar is under Jigyasa program of CSIR, it's my duty to talk to students about the scientific temperament and other things. So this talk is divided into two sections. In the first section, I will be touching on upon curiosity, scientific temperament, and scientific methods. And in the second one, we will take some product. For example, you know that you were driving a car, but it is seldom known that a car, how many different parts it consists of. Okay, so we will be trying to understand that there are different parts made of different materials, and different materials have been processed in so many different ways, so that they bring to product. So these two sections, first of all, I will talk about curiosity and scientific methods. For example, you see, if you go to Oxford Dictionary, you will find that curiosity is defined as a strong desire to know about something, and at the same time, Cambridge Dictionary, it says an eager wish to know or learn about something. In the right side figure, if you see, curiosity is a kind of mental condition where a bell is ringing in the mind, which says that there is a question. You want to understand something. So until unless there is a bell ringing in your mind, you are not curious about something. So what is scientific temperament? So it is defined, scientific temper basically is a word which was first used by Pandit Jawaharlal Nehru in his book Discovery of India. And I'll come to the details of this word, but let us understand what it is. So he says it is a way of life in a society based on an attitude of logical and rational thinking. That means any society which uses logic and rationality in all walks of life, we call the society has a scientific temper. So scientific temper means it's a thought process, and it is governed by a given set of rules of investigation, which indicates that if you want to learn something, the learning process has to have a way. It has to go through a rule, and this we call a methodical way of investigation, which is basically science. So in the process, you in your life, you can keep all your eyes shut, ears shut, or mouth shut, but then we will not say that a person is scientifically tempered or he has scientific temperament. A person who has scientific temperament, he keeps all his senses open always, and he always has a microscope kind of thing, which is just a tool to learn. That means we need to be uh, open, as well as we should always uh, uh, take with us some tools to investigate what we are looking at, provided we have curiosity of understanding and learning. So the third president of USA, he used the word informed citizenry. So he says informed citizenry is the bulwark of a democracy. That means citizens who are very informed in a society, in a democracy, they are the backbone of the society. And once they are informed citizenry, we say that they must be able to understand the scientific development, and for that purpose, they have to have knowledge of scientific process. So what I want to mean here is that a society should have a scientific temperament, and it should have a tendency to analyze the things, whatever it may be. It's not only related to science, but many humanities area also. So let us see what is the significance of scientific temperament. It is to develop a spirit of inquiry within us, leading to search for truth and new knowledge, and the refusal to accept anything without testing and trial. So that is the first and foremost thing we should understand that we should do. And second is to develop a mindset where one can question freely and is ready to be questioned. So there should not be any ego if we do not know something. So we should be ready to be questioned, and we should be ready to ask questions. And also to make one avoid decision making based on precedence only. That means if something has happened in past, then we also will do. That should not be. We will do only thing which are correct and right. And significance of scientific temperament lies in the fact that this helps us in developing the nation in all spheres. It is not only scientific, but political, economic, and social arena also. In the figure you see here, this is a herd, and this herd is trying to paint this different guy in the same color. That means if we do not have scientific temperament, then we will become a part of a herd, and that should not happen with us. And also, in India, when we are living, we should know what are our fundamental duties. And the Article 51A of the Constitution of India, it clearly says that it shall be the duty of the citizen of India to develop the scientific temper, humanism, and the spirit of inquiry and reform. So you see, in 1976, this article added in the Constitution, and how important it is to us that we should do our duties by developing scientific temperament. And second is that we should constantly rise to higher levels of endeavor and achievement for the nation, and we should provide opportunity for education to our children in all walks of life. So with this, let us understand what science is. For any science to happen, we have to have questions. We should be surprised when we look at something. There is in the slide you see left side, an experiment is going on, and the child has a question mark. So he is surprised what is happening somewhere. So that surprise gives rise to thinking process. That is the thinking process starts from there. And once the thinking process starts, the child starts thinking in many ways that ideas come to him why something is happening. So he starts hypothesizing that what must be the reason for what I am surprised of. And then uh, to he hypothesizes so many things, and then he wants to do experiments and test whether what I am thinking is correct or not. And so he goes to do experiments, and during the experiments he does everything, and he sees what is happening. So he has the curiosity, and he has the tool to observe what is happening during the experiments, and then he records all the data and analyzes it. After the thorough analysis of the data observed by him, he concludes and writes. In a scientific arena, we call that he is writing a manuscript. Okay, but actually he is writing the conclusion that he has found that this happened. Whatever he was surprised of here, he has found an answer that it is not a surprise, it is a science behind it, and so he writes here. So for what happens, the results and conclusions obtained of these experiments are for the society and must be accessible. This is what is my opinion, that whenever we do research, it should go to the benefit of the society and it should be known to people, and people should be able to understand that yeah, it is the scientific new information or knowledge, and all these knowledge then come to our books, our textbooks. If somebody says what is Boyle's law and Charles' law, then that means Boyle and Charles, they would have done all these things to do experiments and conclude something, and this is why you see these laws in your textbook. And here you see there is a bicycle, and this bicycle doesn't have pedal, and this was made in 1820 by Dr. Karl von Drais from Baden, Germany, and it is there in the museum. But you see, this bicycle has come to uh, this bicycle somewhere in 1900s, and then it modified slowly based on the requirement of the people, and it came to a folding cycle. So this is the development which we have witnessed in our life up to now. And why it happens? Because we want comfort, and for the comfort there is a necessity of something, and also we want it to be affordable, not only economically but by our body, mind, and spirit, and this leads to innovation. So you see, scientific knowledge and inquiry of spirit, they lead to innovation. And today, if you see around us, what happens? Uh, this is left side. You see, this is then long back. This is what we used to see earlier. This is the life earlier, and now we have all the new set of products. That means these products are the result of the all-round research work done by scientists around, and so we got it. Okay, so if we want to progress as a society, then what are the things we must do in our life as a student, a teachers, or a general citizen of the country? So we have to have a spirit of inquiry, or scientific methodology of investigation should be made a joyful pursuit for all of us. We should enjoy doing science and using scientific methodology to look at the things. And this is applicable to our home. It's not only that in a scientific laboratory science should happen, or in a school it should happen. It should happen in our home, in our surroundings, in the society, in the nation, and the whole world. It should do. And it is not only the physical sciences and natural sciences which requires this kind of investigative way of uh, scientific methodology, but social sciences, economics, psychology, law, and politics, history, all are equally important when compared with natural sciences and engineering. So even in our society, when we see that something is happening, we should be able to analyze scientifically why is this kind of thing is happening. For example, everybody says that traffic problem is there, but why it is happening? What are the psychological reasons? This requires a scientific kind of investigation. So this is the backbone around which the life of a nation is built and grown. So with this, I move on to a new set of materials or products which generally comes around us. And here you see we generally use utensils. We go to market and see handicrafts, rails, wires of copper or aluminum, and then you would be able to see that there are many trucks on the roads carrying this steel sheet or plate coils, trucks uh, which are trucks are there which has this rumbles coming on out from this. Then excavators are there. So you see what is happening. This is very hard material. When this truck takes this hard material, what kind of bucket it should have? Or here, if this is a sand is taken out from this bucket, then what kind of material it should have? So each and every product what we see around, they have materials, and these materials have different properties which must be there for this to withstand long working and long life. Okay. And similarly, we have jet engines where we need high temperature materials. For example, these transmission lines, we want to have high conductivity of aluminum alloys where we can pass on high current, and it should not sag. You see this all the wires are sagging, going down. Why it happens? Because the high temperature due to high current transfer, and due to high temperature they have become soft and they sag. So we want to have a material which is highly conductive, as well as it should not sag. It should have high strength at high temperatures. Similarly, car body, we are now vying for the condition where we should have a car body which is with high strength, as well as low weight. So a specific weight of car should be low. So what kind of material we should use for car body and all this. So these are very common products we see around, but we do not generally consider or consider to think what they are made of, and what are the development taking place in all those areas. And this is where the curiosity and scientific temper must be developed, so that we generally look around and decide and learn about the things. So materials, when we talk about, there are basically three different categories of materials. One is metals. We say metals and alloys here. Metals are pure metals, and alloys. There is a base material, and this base material is added with some other elements to give some better properties to pure metals. So this is called alloys. Then we have ceramics and glasses, polymers. There are three main categories. And then there is a category of composites. Composites means a composite can show the properties of two or more different materials. For example, if you have metals and alloys, metals and polymers, then this is a composite, and here you can see, the tires, they have steel wires or mesh, and they have steel cord tires. Here you see. Similarly, the buildings what we see, they have bars, steel bars and cement, concrete. So this is a composite basically of metals and ceramics. Similarly, car body, if you see, car bodies are nowadays, they are thinking to make it by composites of ceramics and polymers, what we call carbon fiber reinforced plastics or glass fiber reinforced plastics. Okay. So now, what are the properties these give together? For example, metals, they are soft, conductive, they have high structure strength, and they are ductile, and they are heavy, and they can be used only at low temperature. But ceramics, they can be used at high temperatures, but they are brittle. Okay, and polymers, they are soft, they have low modulus and low strength. Similarly, glasses, they are non-crystalline solids. Non-crystalline solids, I think I understand that you understand what crystalline and non-crystalline is. And so when you have combination of these two or more materials, then whatever material is made out of two or three materials, they give the properties which are the combination of the properties of all the mixed materials. And if we see what are these different materials are, then I can say there are two different kinds of materials. One is structural material. We call them as a load-bearing materials. Means materials which are required for bearing loads. Yeah, for example, buildings, cranes, all those things are cars. These are the materials which bear load. So key properties what we should look into these materials are elastic modulus, yield strength, ultimate tensile strength, hardness, and all those things. And in some cases, what happens that metals deteriorate, they corrode, or they wear. So we also consider these things, these properties also in load-bearing materials, because the load-bearing capacity of these materials may deteriorate based on the corrosion or wear behavior or losses of these materials. So the second is the functional materials. So functional materials basically display specific or useful physical properties. So whenever we talk about physical properties, then for example, optical properties, electrical properties, dielectric properties, all these things are functional properties which must be developed in the material depending upon the need of the product. Here you can see this is a aeroplane, and what will happen if the wings and the material used for the wings have low elastic modulus. So it will bend like this. If it doesn't have it is not strong enough, so they will deform like this. And if the fracture toughness of this material is low, then it can break. Or if it is very heavy, density is very high, in that case, it will bend like this downwards. So you can understand that if a material is to be made, it has to perform some service, and we have to test that material so that they can perform according to what we want. Similarly, this is the mechanical properties, but here, if we want to use a material at high temperature, high service temperature, so as you heat it, if it is soft, it will bend. So your material should have high strength at high temperature also. So this is one property, or thermal conductivity. Here, in some cases, you may want that heat doesn't go inside this, and in some cases, you would like that heat should go faster in this pan. So you have to design the material such that your thermal conductivity is low and high in this case. Similarly, magnetic properties, you would be seeing transformer around your houses, and these transformer have soft magnetic properties. At the same time, permanent magnets have high magnetic properties. So what I mean is So all these materials, what we require for our application, they are made out of different materials and different processes are used for making these materials. Similarly, I talked about this lateral conductivity of transmission lines. Then thermal expansion. Here, in this case, if you heat it, it will bend between two restricted platens. And if the thermal expansion coefficient is very low, in that case, there will not be a large change in the dimension. Now we'll look at the level of structures. So structure levels are like that it can go from subatomic scale to macro scale. This is the size you can see. Very small size, and this is around 1 meter. We call it macro size. So the properties, but just say if we are looking for mechanical properties, then it is affected by this scale, nanometer to macro scale. But if you want to have nuclear properties in the material, then you will have to consider the structure level up to the subatomic level. So this is the structure level or structure scale which determine what kind of properties you are looking for and what kind of scale you should be investigating to achieve these properties. For this property, this is the scale, and for this property, this is the scale you should look for. Now, how to look for it? For example, if this is a cycle, bicycle, and we want to know what is there inside this, what it is made of, then what we do, we will cut it and polish it, and after that we will take a sample from here, and then again we will take it to microscope and see what is there inside. So it may be possible that we have this structure or this structure, but if this structure is still not resolvable, so what we do, and we further increase the magnification and see that okay, in these small grains, what we see here, there are some precipitates, we call it precipitates, and these black areas where we were not able to see anything, there is a lamellar structure inside. Now further, if you want to look at this area, then we should go to TM, transmission electron microscope, and see what is therein. And similarly, by doing this, by high resolution transmission electron microscope, you can look at the atomic level of the material. So once you know that this is the structure of this material making this cycle, now if you want to improve this bicycle by making a new material, then we should be able to understand what are these features in the microstructure and how to modify the material so that the new structure what we get, they can give better properties to make a bicycle which is better. For example, lighter cycle. So you have to make a material which is lighter. So you have to change the composition. At the same time, you will have to look for the structure which can give the strength. So structure of the material is determined by the strength, determined by the composition, and the properties what you get. You can always test the following properties. You can test the material in tension, compression. You can bend them. You can give a torque to a material, and you can deform at a slow rate or a high rate, and you can test them at high temperature or low temperature. You can test them on impact loading, cyclic loading. So all these things we do to understand the material and to design a new material for a new application overall. Now, if you look at the material development evolution through the history, then you will see that around 50,000 BC, the metals, only gold we know because gold existed as it is. Gold, ceramics and glasses, they were stones, shells, bones, all these things were there. And natural materials like wood and other things. So we depended on basically naturally occurring materials, and we had only few candidates, candidate material option. Now, with time, we added silver, bronze, iron, lead, copper, all those things in metals, and similarly, we brought in concrete and all those things. And here also natural materials also the area improved for a cork, for balsa, and grains. We understood that different orientation of grains of woods will be giving better results in properties, so increasing the candidate materials. And then uh, today we have large number of materials available to us. Here you can see nickel alloys, titanium, steels, tungsten, carbides, aluminum alloys, copper alloys, composites. All these things have made our life very easy in choosing a new material for a new application. Even then, even today, we are engaged in developing novel materials, though we have this. So what is happening is that we are able to decrease the density. Here you see metallic foams, polymeric foams we are making where the density has gone to very low level, and we are able to make these materials. So what is the demand today is that we want to have materials which are low in density but high in strength. So most of the research work in materials basically for a structural application, they are heading towards this area here, in this area where you can have low density and high strength. So this is the area where people are trying to develop materials. And then I will be talking mainly on metallic materials here now onwards. Here, if we talk about metallic materials, we have two broad categories like ferrous alloys and non-ferrous alloys. So ferrous alloy, we have carbon manganese steels and then stainless steels, and alloy steel where we use, for example, molybdenum, titanium, vanadium, and other tungsten, all those materials, low alloy, high strength low alloy steel, advanced high strength steels, marazine steels, tool steels. So large number of steels and cast irons are available for us, and a lot of development had already been taken place long back in 1900s. And non-ferrous alloys, we have aluminum alloys, copper alloys, magnesium, titanium, nickel. Magnesium is one of the lightest materials, metallic materials, what we are looking for today, but not very efficiently. We have been able to do, but we are still trying to. So titanium and nickel alloys, they are very good for aerospace application and defense applications, and because they are corrosion resistant and high temperature strength is good for these materials. And they are refractory materials. These are used for high temperature application basically. I did try then nowadays instead of ferrous and non-ferrous, where here you see in aluminum copper, we say aluminum alloys, that means aluminum will be around 90% and less than 10% will be copper, or means there will be a base material aluminum or magnesium or titanium, but there is a new development in alloy making, that is today it is known as high entropy alloys, and it was first developed in 2004 reported. Here there is nothing like there is any principal material, aluminum will be 90% and copper will be less than 10%. It's not like that in high entropy alloys. In high entropy alloys, the composition is something like, I will just write it here, just say this is a triangle, and this is aluminum, this is copper, and this is magnesium. So if any material is made of these three elements, then when we say aluminum alloy, then aluminum will be large and magnesium and copper will be very small in amount. So we will be talking about this. But when we talk about high entropy alloys, this alloys basically lie somewhere here. So all the elements will be almost in equal proportion. So this is a new alloy system. A lot of people in the world are working in this area with very good properties, which are surpassing all the ferrous as well as non-ferrous alloys. So with this, I go to Pragati. I think I have half an hour.
Yes, sir, we have.
Okay. Okay. So now, if we decide on the composition of a material, and definitely we would like to go take the material to a function here. So it has to perform a function, and this function would definitely be there as a part of a product, and that part will require some shape definitely, and it will require some properties. Okay. So to achieve the shape and properties of a material, to perform a function, the material should have a given structure, as I talked to you earlier, and this structure is very much amenable to the process what we adopt for making this material for performance at this level. That means, though we select the material, but the process is equally important for the material to perform the way we want. Okay, so now let us see if you have materials. Materials can be in 3 different forms: in bulk form like this, or it can be in powder form, it can be in wire form. Now, if this material is required for any application, then definitely you will shape it, and once you want to shape it, you can do in 2-3 different ways. First of all, take the bulk material, make it liquid, heat it, make it liquid, and then give a shape. Or you heat the material and it becomes softer, and then apply a force on this to give a shape to it. That is also a possibility. Or take a powder of wire. Powder will be different. Fine particles. Then fine particles can be maneuvered into a given cavity, the shape of which will be similar to a component shape. We call it powder metallurgy. So liquid to shape, melting and casting, and heating, or in the cold state, we shape the material, then it is metal forming. Or from powder to a bulk material, we do powder metallurgy. Sorry, metallurgy. And then there are some new advanced techniques of spray forming and additive manufacturing. So what we will do, we will be talking on these things, how to shape a material, and at the same time we get the desired properties. Here this is a casting process where you have a cavity in, and this cavity is for a product, and you will make a liquid of material and then pour it, and then you get the liquid goes in, takes the shape of the cavity, and then becomes solid, and you get the product. Similarly, this is a forging process. You heat the material, make it softer, and then you have 2 different dyes, and this dye, when they come together, they will make it give a shape. Similarly, there are 2 rolls, we call it rolling, 2 rolls, and they have, for example, the 2 cavities, and with these 2 cavities in these 2 rolls, you can give a shape of this. Okay, you can have no cavity at all, the surface can be plain, then you can have a plate or sheet here. So rolling can give you different shapes. Also, there is extrusion. By using extrusion process, you can make rods or tubes. You heat the material. Here is a ram. With this ram, you push it and you get the material. Similarly, as I was talking about powder metallurgy, so powders are compacted apply a force within a die, they are compact. Once they are compact, then you put it in the furnace, all the particles, whatever were there, all the particles will come together, and finally, after diffusion at these places, they will merge together, giving rise to a bulk material like that. So this is called powder metallurgy. And spray forming, I will talk to you in detail in the later slides. In this talk, I thought that this is for students, so I will use some videos, and these videos have been taken from internet, and this is only for educational purpose. So we will see these videos one by one, and then uh, it will give a better idea to you whatever I explained just now. So here you can see this is the process of melting and casting. So here this is the mold. This is the cavity you want to make. This is the pattern. You put sand in, take the pattern out. Cavity is there. Put the melt in. Melt is solidified now. Take it out. Take the product out. Like that. So you get your product. Similarly, in forging process, here there are two dies. Material is heated, and this material is being deformed using two dies. This is called open die forging. Now we see closed die forging here. And closed die forging, if you see, there's a cavity, bottom die. Now you put the material, the die hits, then again, and then you get the product. This is the connecting rod for automobiles. Okay. Now you see what is how the rolling process takes place. This is a slab. Slab is going through two adjustable rolls. Like that. This is three high roll. So bottom roll and middle roll is rolling, and then the runout table goes up, and then there is reverse rolling. Yes. And then there is four high rolling mill. This is basically used for thin sheets. Billet is fed into two working rolls. There are working rolls and backup rolls, and here you can get thin sheets. Okay. Now we go to new videos. This is for rolling, as I showed you. This is a billet going through a roll. Roll is having a cavity, and the different rolls will have different cavities, and the shape will be changing together, and finally you get a rod or whatever you want. So depending upon the cavity you have on the rolls. Then this is a wire drawing process. How you make wires. Here, this wire is this rod is going through some cleaner as well as lubricant. And here you can see the material is larger diameter is decreasing to a lower diameter. So it is going through a die. And this process continues for so many different dies so that your diameter is reducing in each and every step of die wire drawing. So wire is drawn through the dies, and you can have very large diameter wire rod to find wires. Here this is a video for extrusion. Here you can see this is a billet. Billet is heated red hot. It should not be red hot, but it's heated. Then cut into a size. transported to the extrusion press here, and it is a heater and the rime is coming and the material is going through a die, and you get the extruded. You can have rods, you can have tubes, you can sections, anything you can have in this. And in this process, the last video is on industrial process of making sheet coils. Here you can, sorry, here you can see this is a slab heated, and it is going to descaler where all the scales generated are taken out. Then there is roughing mill where the thickness is reduced as well as scales also go away. And then intermediate stand for rolling. Little bit of cooling of the material. Then it goes through a different rolling stands. Now you can see, and the thickness of this will be reducing slowly. Okay, first stand. In the second stand again, now every stand thickness is going down, and then finally it is cooled in a cooling section with water spray. And then you measure the thickness of the sheet, whether you really achieved what you wanted, and then you make a coil of it. So this is the process of steel sheet coil. The coils what you see in your city, laden on trucks. Okay, and not only that, this rolling process, once you heat it and it goes through within the rolls, it has initially it has a size of grains very large, and then it is thickness is reducing, and then finally you have a smaller grain size. Okay, so there are two purposes of rolling or any deformation at high temperature. That you reduce the size to get better properties, as well as you can try to have different shapes of the material. For example, this is for rails, and this is for pipes, this is for strips, like that. So different input materials are required for these purposes, and these input materials are, if they are flat like that, we call them slab, and if it has a smaller square cross section, we call them billet, or a square large section, we call them bloom. Okay, and similarly, if you see how utensil is made. So we visited one area in Bankura in West Bengal, and we saw that people in village, what they do. So when you see this thali, then you should understand that how many steps are involved in making this. The villages, they first melt the material, then cast it in this shape, and then they again heat it, and then one heat and then roll it. After rolling, they stack so many different sheets like this and roll it together, and then they cut the edges, and after cutting the edges, they heat it and then deform it like that, and finally they face it and make designs on it, and then this comes to the market. So this is what I wanted to mean here is we are trying to I'm trying to convey a message that whatever you see around, you should have a kind of investigative mind, so that you understand that what are the efforts and has gone in, and what should further effort be, so that we get the better option of these things. Now this we understood up to now that what are the casting, rolling, extrusion, forging, and drying processes, and these shapes are very simple. Now, if we want to have better shapes, such complicated shapes, for example, this is for heat exchangers, where one liquid will go through this, other liquid will go through this, or gas will go through this. Here in this system, if we want to have a cooling system where we have this coil inside the empty means channels, then how should we make it? These processes cannot do it. Or if we want to have a replacement for our thigh bones, bones are like that, porous. Then how to make this kind of material? So for that purpose, there lies a new technique called additive manufacturing. And for example, if you want to make a shape like this, generally casting you have seen, by casting process you can melt a material. This is a die or mold and then put it and then take it out after cooling. Or by machining, you can take a block like that, you start machining it and come to this shape. But for in additive manufacturing, you try to make the same shape by layer like that. So you take this shape and make a computer model, and in computer model you try to divide this in so many different layers, and then every layer you know that what kind of cross section it should have, and using this technique all the cross section will be printed one by one over the other, layer by layer, to reach to this final section. And just to have a feel, here different layers are coming together and making a 3D model. Okay. Now again I have 3 videos just to show you how this works. Here you see this is a 3D printing of polymeric material, and it is printing layer by layer of a given shape which was made on a computer, and that data has been transferred to this machine by in terms of different layers, and the machine is printing layer by layer a product. Now you see what is the product then. This is how a 3D printer works and give this 3-dimensional product. Okay. Here, this is a 3D printer of metal material. We call it TET, where we should see from beginning. There are 2 powders coming in. There is a laser, and material is melted in this region. And the powder melted, they are being deposited one over other to make a 3-dimensional material. Here you see. These videos are meant only for students to understand, to visualize what it is. Here, it is not wire or powder. Powder is fed. You can see here. There is a product here. One layer by layer, powder is coming and laser is melting it. And finally, once it is done, all the computer model products are in 3-dimensional pictures. So this is how it is done. Now I come to actual procedures here. This is how it looks like. And there is a powder here. Powder comes here first. This would be at this level. Powder will come first here. The first layer will be printed here, and then it will come down like that. And then again powder will come on the top, and then again second layer will be printed. So layer by layer printing of this will give rise to a cup like that. And this you have seen 2 powders. You can have 4 or 5 powders coming together and melting it, and this is how it looks like. There are other ways where you do not melt the powder. What you do is you take the similar way, instead of laser here, you put a binder. So this binder comes in and all the powders without melting, they just join together in, we call it green condition, like that. Once this green condition is there, and then if we heat it, then it is called a sintered state, and we get bulk material with good strength. Now there is one more area of spray forming, where if we want to have a very fine material with better properties, this is a cast material and this is the fine material. If we want to do this, it is very difficult to do it by conventional processes, what I discussed earlier. Then spray forming was developed like this. Here you see, there is a liquid, liquid is poured, there is a gas coming out, this gas interacts with this liquid, and this liquid is disintegrated in so many different droplets, and these droplets are deposited here. So this video is, I have seen this video, this is my own experiment, and here you can see that how the metal is disintegrated and deposited here. And this experiment, what you are able to see here, this billet is the product of this experiment. So here, this product can have these properties. So in a single step of spray forming, what you are able to get is, this is as cast, but to reach from this to this is very difficult. But by this process, in a single step, you can reach to this structure, means the very fine structure. Now this process can have several variants like that, where same thing, all these powders can be fed in between two rolls. We have already discussed. So spray as well as rolling. So you can get sheet, very fine sheet in one step. Similarly, you can have if you don't want to use gases, then you can use some pulsator in liquid. This is a perforated disc. You can have droplets and it can deposit. If you want to make a tube, this is rotating fast and liquid is coming in a stream, and it is getting diverted to the surface, inside surface of a big drum. Then you can get tubes also. Also, you can get bimetals by using this. If there is a single spray, and you can have two sprays together, and once you have two sprays, then you can have bimetallic materials, and these bimetallic materials you can roll it, and after rolling you can have dense material rolled together. Now the last section of this, I will take just 5 minutes more. You know that when car make an accident, they hit together and damage together. So if there are two cars, and if you have a steel rod in between, for example, cars will come and hit this steel rod, and same movement of this car will be transferred to this, because steel rod will be very hard. It will not bend or absorb energy of this car, and the driver in this or this will be affected heavily. But if you have a foam material inside, in between, where the foam will be very soft, and if the car hits it, then all the energy of this car will be absorbed by this foam, and then the impact force on this driver will be very low. So foam is a very important material for automotive applications. And just to let you know what foam is, here, this is a metal foam, for example. It has 75 to 95% porosity. It has energy absorption capability. And also, if you have noise can be attenuated using these foams, and it is vibration damping can also be achieved. Okay, so here you can see this is a closed cell form where each and every pore is closed. Okay, so if you want to pass gas or water through this form, you cannot because each and every pore is closed. You can have open cell form where it can pass on the gases and liquids through this, as you saw in the previous lecture, previous slide. So now what we did actually is like that. Here we try to have a powder of aluminum, and this is a foaming agent which when added to this, and then we mix it. After mixing these two materials, we fill it in the tube and forge it, and then finally what I mean is these two materials come together and we employ some process and we make sheets like that. Very fine thin sheets are there, and these thin sheets will have a structure of like this material of this powder like this solid, and this foaming agent will be somewhere like this inside this solid material, because we started from two powders and we made a solid, and this is a larger amount of powder, and this is a foaming agent, very small amount, around 0.2%. So they will be somewhere lying in the solid. Now if we heat this solid, all these foaming agent, they will decompose, giving rise to gases, and these gases will make it foam like this, like this. And here in this, you are saying, let us see from the start, it was very thin, and then in the furnace, it is foaming like this. So this is how a foam material is made. And here you can see after 0 second to 116 seconds, the same foam material started from here, this reached to this thickness and then died out. So we have to, if we wanted to have a foam, we have to take this out from the furnace in a very short time. These are the materials, foam materials we have made in our laboratory. And with this, I thank all for patience hearing. Thank you. And to all the students, I will say, think calmly, build a strong foundation of your studies,